domestic water main. So you have all those objects that are in the picture, but they are not the reason of the picture. So in this case, they gave a name to the picture, but it's domestic water main.pkg. This even hurt more. Are you going to look, if you are going to look for this column in the folder that have the pictures about water pictures, the water main pictures? You say, no, I'm looking for columns. So either you create a name of the picture that has all the objects that you have in the picture, like the name of this picture or a label, it has column, still column 13, column 22, beam 09. So you have to look at all the objects in the picture and name them. Who's going to do that? And just to have an idea, this is any undergrad student here? Okay, no undergrad students, so I can tell that. Okay. This is a summer research for undergrad students. Okay? I got them 5,000 pictures and asked them to count how many objects was in the picture. Okay? That's fun, that's research. They have to learn how to do research. Okay? So look, they came up with pictures with 0 objects. Those are the ones that by accident you take a picture of the floor or something like this and it's in the database. Okay? The sky. And pictures with 300 construction objects, but you came with a mean of 45.4 objects in the picture. So this means that you'd have to give 45, in average, 45 tags to your picture. So either you do this automatically or you can do it. So again, now the solution is now not data mining, not traditional machine learning. So you have to go to robotics, computer vision, try to understand. We extracted feature representation of all the pixels in a picture, was able to segment the picture, get a signature from those pixels, and then create a database of signatures of materials. So you could know this is concrete, this is steel, this is. So you are just reducing the search space. So if you're looking for a column, you know that's concrete. You have to all pictures that show concrete elements. We created information about the position that the camera was. So all the objects that are behind the camera cannot be shown by the picture. We created information about the data that the picture was taken and superimposed with the schedule of the project. So if the column was built in October 15, just pictures taken after October 15 could show that object. So we start creating all these and you have the same thing, find images, and you go, you select the object, and you retrieve every picture that shows those objects. So it's the idea of drawing on data. There's a lot of things to do to deal with and organize data. Then I moved to Carnegie Mellon. Carnegie Mellon hired me as a faculty when I left Illinois. I loved Illinois, no problem with Illinois, but I don't know if any of you ever lived in Champaign, Illinois. So it was a little bit tough on family, so I had to move. So I went to Carnegie Mellon, and Carnegie Mellon was starting a new group called Advanced Infrastructure Systems Group. Okay? Their interest was to deal with the aging infrastructure and making smart infrastructure. And this is really data-rich environment. What they mean is that you have the example of a bridge, the bridge collapsed here. The analogy that they use at Carnegie Mellon would be the human body. Okay? If you have a pain on your knee, you don't go playing football. But there is a lot of things that comes before. You have your knee, a pain, this is a sensor system. Okay? The pain is a sensor, so it's telling you that you have a pain. But then your brain makes a lot of decisions related to that signal that you receive, pain. Oh, it's a small pain, I'm okay with that. I'm going to get a little bit of ice, and then I will try to play. I think that after the ice I'm going to be okay. No, it's a terrible pain. I really should not go, but let's wait for tomorrow to see if it's better. No, this is really, really bad. I'm going to the hospital. So you have a lot of things that you do. It's not just to sense the pain, but you have a brain that makes a lot of decisions. When you talk about smart bridges, a lot of people are electrical engineers that just think about the signal and adding the sensor. But that's the small part. You start having a lot of false alarm. You have something different in the bridge. Yeah, but what this something different means? Should I close the bridge? Should I just call someone to come and inspect and see if everything's okay? Should I get a huge alarm and get everyone out of the bridge? Is this risk of collapse? So that link is missing. So that professional today doesn't exist when you talk about those things. Someone that really understands about the sensing and really understand about the bridge and link those things and can decide how many sensors do you need, where to sense, and how to interpret the signals. This is failing. We are failing on that. And this is where Carnegie has a lot of interest of training those professionals. Civil engineers in the masters learning signal processing, learning electrical engineering, hardware, sensor programming, being able to build those systems with big understanding about everything. So then we started again looking at this big picture. I left a little bit the construction and went to a bigger domain that it's operations and maintenance, not just construction of all infrastructure systems. And this is very related to James' research that he does with pavements. There are other areas that are concerned with cracks and other things. So this is a company called Red Zone Robotic, came to us. The student was Wei Goose. She's now works at IBM Research Labs as a computer vision person, and Jim Garrett, that was my colleague there. So the idea is that this company had this robot that they send down with solar pipes. Okay? So there is something interesting happening in the US. Cities, old cities like Boston, New York, Philadelphia, Pittsburgh, their solar network is in terrible shape. And it's very easy to see they are in terrible shape by measuring the quality of the rivers next to the city. So you have what they call overflows. You have a rain, the system cannot deal with, and then those overflows under the river, you measure the quality of the water, you say, solar came the water, who is responsible for solar? Department of Water and Solar. And they send them a fine. So cities like those old cities were paying millions of dollars a year on fines. Very expensive. So what they did, they went back to EPA and said, look, we're spending so much money to pay your fines that you don't have money to fix our network. It's a chicken and egg. You get all our money on fines, you have no money to, and then you're going to pay more fines. So what we need you to stop fining us and let us use that budget, the $10 million a year that's spending on fines, into at least mapping and seeing the condition of our network. Because it's underground, you don't even know how this network looks. And then the EPA said that makes sense, and signed with those cities something called the consent decree. Okay? They said, okay, I'm not fining you if you spend at least $15 million a year into mapping your network. So now there was, from one day after this law was signed, there was several cities that had to inspect, and those guys, robotic companies said, hey, nice business. So they jumped into the business. This Red Zone Robotics, their business was to inspect nuclear power plants after accidents. So they developed the robots to go in Chernobyl, in those places. So it's not a very good business. It's very cool, but you don't have enough nuclear accidents for those guys to justify their business. Okay, they have a business every 20 years and they sit for the rest. So that was not a very profitable company. So when the guy saw this, they said, hey, I can use my robots there, and there is business to be done. So the guy jumped into the business without understanding pipes. He understood robots. But the idea is that he would send this robot down, and there is a trailer with all the cameras, and this is a tethered robot that someone drives the robot with a joystick, my son's dream job, work with a joystick, like a video game. And then they had those pictures coming from the robot, and then they would geocode the whole information, not different than the James does with highways. And then you had those circles. Those are points of the facts. And these were done manually, not automatically, by a human. The human was looking at the image and said, oops, a problem. We'd stop the robot, turn the camera, look around, and take several pictures, and then classify the defect. And the circle is how bad the defect is, ranking from 1 to 5. So this company would not sell the robot, would sell this to every city. They go a service, they would go to Philadelphia and they would map the whole thing and they charge millions of dollars for this information that the mayor would look with the water authority people and would look at the condition of the network and would decide what to fix and where to fix and how to fix. Okay? So this operator would develop this thing using a standard, national standard, it's called PACP, Pipeline Assessment and Certification Program. So those guys are trained and learn how to see nasty thing 24 hours a day. Okay? I cannot imagine it more. You feel the smell by looking at those images. Okay? It's disgusting. We did a lot of lunches, meetings, looking at those pictures. So we have the whole, this is a subset of the thing, but you have very complex ways. You have structural defects that can be a crack, that can be a circumferential crack. You have maintenance, you have deposit, you have vermins. Okay? You have roots, okay? You have rats. Rats, it's a defect. Okay? So they go to those things, and obviously the human goes and classify those things, and you have all the defects in the system. What happened is that those guys developed a new robot. This first robot was $1.5 million robot, and they would not sell. They sell the service. Then they came, that was the responder. Then they designed the Solo, a $10,000 robot, autonomous. You drop it in the manhole, it goes, comes back, and you grab it back, and you have 2-3 hours of data. Okay? So now cities start buying it, and they are selling as hotcake. Okay? Hundreds of those solos. Cities like LA bought 150 solos. So they have a pickup truck that leaves Department of Water and Power in LA in the morning with all those robots, put in several manholes. At 10 a.m., 11 a.m., they come back and they retrieve all of them. So now each one has 1-2 hours of data, and you have 150 of those. So at 10 a.m., you have 150 hours of data. Okay, pretty cool. So now the guy in the trailer has 150 per day, 300, 400 hours of data generated per day, and he has to look at those data. Where? How? So now those guys said, we have all the data. We don't have enough PACP certified inspectors to look at all those videos and to classify. There is not enough people. They start sending the data to India and having engineers in India doing the classification. And there was a lot of issue because the training was not well done, the certification. So they came to us and said, you have to automate this process. You have to use computer vision and find a way to do this classification in an automatic way. You cannot deal with that. So the interesting thing, I'm going to rush, I don't have a lot of time, I had a lot of interesting research to present, but the interesting that happened was a very difficult problem. James knows about that. Just crack by itself, it's complex enough. If you have rats and vermins and other things to do the whole classification, was a nightmare. And we failed and failed and failed and failed again. The student was crying every day. Until one day you had a click and you realized by looking at the images, you had miles and miles of good images. Nothing in the pipe. And then you had defects, clusters of defects, and then good pipe. And then we decided we asked the way to measure the whole frames, pictures that we have. Tell me how many are healthy images and how many are images with defect. And she came with a perfect Pareto distribution. It was 80% of the images had no defects, 20% of the images had defects. So I said, so I don't need to do a classification at the first step. Can I do a detection algorithm? Just detect that something is different with those images that are not a healthy pipe. And this is very easy to do by subtraction of pixels. You have what is called the good image, and you get the other image, and you start subtracting. If you have difference, there is something there. So without doing classification. So we use the SIFT, other things, I don't have time to go here. But the interesting thing is that yes, we are able to do it. And the beauty is that if you have now 100 hours of video, by passing through our solution, you reduce 80%. So you tell the human inspector, you don't have to watch 80 hours, just watch 20 hours and tell me what is in those 20 hours. The other 100 hours, I know that there is no problem. So it's a saving of 80% of the time of the inspector. So the company was pretty happy. And the Popular Science considered one of the 25 new technologies from the infrastructure here. So had a huge impact and good patents. Then the government came to us and saying, even more complex problem with data, how people are drowning in data. This was right after Katrina. They had a very interesting situation. The Secretary of Energy was visiting with President Bush the port of New Orleans, and he was informed that the port was going to be closed for reconstruction for 6 months. The Secretary of Energy looked at his staff and said, oh my God, what's going to happen with Florida? And everyone said, you're here in Louisiana, New Orleans is completely destroyed, and this guy is concerned with sunny Florida? What's wrong with this guy? But again, the guy had a very interesting aspect. The issue was that the coal that goes to Florida, to be burned in Florida, comes from Wyoming. It comes from Wyoming by train, moved by barge in the Mississippi, back to New Orleans to the port, back to train to Florida. So if you cut the port, you cannot move the coal to Florida. It's not so easy to say, no, get another mine. It's not how it works. A power plant, it's set for the amount of sulfate from a specific type of coal. The filters that avoid pollution are perfectly set for that coal. If you change the coal, you have to change the whole filtration system in the power plant. This is a huge investment. So those guys, they are locked to one type of coal, and you don't find those coal wherever you want. So you have to use that coal. And the other answer is that, so find another route. You guys in transportation know that the railroad system in the United States is not like this, okay, let's bring another 1 billion tons in that rail lines are owned by different companies. They are already working at capacity. You just don't go like this and you reroute that. In the end, the only solution was to bring the gold from Colombia to the Panama Canal to Florida at a cost of 3.2 times more expensive than the gold that they were buying originally. And they had to do it. So energy, you cannot raise the price. So this was a negative cash flow for the government for 6 months. So what happened is that we have what called systems of systems. Okay? The electricity grid, if the transportation grid collapses, the electricity grids collapse. You cannot feed coal to the electricity grid. And if the electricity grids collapse, you don't have how to run the railroads, the whole controls of the railroad. So all those systems are coupled. And we optimize them if they were individual systems. We teach students transportation, water. If you have a water main breakage, you flood a highway, you stop the water distribution, but you stop the transportation. So all those things in cities in the country are so coupled, and you have the domino effects, and very few people understand those domino effects. What we call the interdependency of energy and transportation systems. So the problem is that EPA, the Department of Energy, had what they call the emergency team in West Virginia, in Morgantown. There is a national energy lab called NETL, National Energy Technology Lab, and they had an emergency group of people that would be called when a hurricane is reaching the United States. And those guys were called to predict how that hurricane would affect the transportation and the energy network in the US. So those guys received 75 different databases to work with. Okay, those are our database came from Department of Bureau of Mines, of coal production, Department of Transportation, private railroad companies, electrical grid, power plants that are private, that have their inventory information, and all those things. So they had all those databases, and they had to do a query in multiple databases. And it would take them 10 days to do it. The hurricane is 2 days away. Okay, and those guys would start with 10 days analysis. And worst, there is the guys that would come with the path of the hurricane. It's a group called the Hurricane Center in Miami, in Florida. No, it's Miami, it's in Florida. Florida Hurricane Center. Those guys predict the path of the hurricane. This is what you see in CNN, the hurricane path. The problem is that those guys move the path every 1 hour. Every 1 hour they come, okay, turn it 5 miles to the south. So you see in CNN, those guys are always, oh no, I was going to hit, but it turned it right here. So those guys are working with 75 databases in a work that takes 10 days for the input, for their analysis changing every hour. So they never ever give any answer. They're just there wasting their time. So they came, you have to do something in real time. So you have to solve this problem. So we came, we created data warehouses from all those databases, and then we went to a system, very visual system. The contribution research-wise was what you call a geospatial data warehouse. There was no data warehouses were not to be geospatial, so we created a theory to integrate GIS to data warehouse. An interesting thing that we finished the research, and 3 months later, a GIS company had their own solution that was better than